We live in a world filled with uncertainty. Every day we face small questions of chance. Will it rain this afternoon? Will the bus arrive on time? Will my favorite team win the game? For most of human history, these questions were left to fate or to the gods. People saw the world as a place of mystery, where events happened without clear reason. A ship might return safely from a long voyage, or it might be lost to a sudden storm. A harvest could be plentiful, or it could fail completely. These were unpredictable turns of life, to be hoped for or feared. This way of thinking began to change, slowly, at first. People started to notice patterns in the chaos. Gamblers around a table with dice. Our story truly begins in the year 1654 with a puzzle. A French nobleman, the Chevalier de Marais, an avid gambler, faced a problem he couldn't solve. He was playing a game of chance that was interrupted before it finished. The game's rule: the first player to win a certain number of rounds would take the entire prize pot. But what happens if the game stops early? How should the prize be divided fairly, given the current score? This was born in the smoke-filled gaming parlors of Paris, and yet its solution would change the world. The Chevalier took his puzzle to Blaise Pascal. Pascal, mathematician and philosopher, saw it differently. He recognized it as a question about expectation and fairness, not just money. He imagined all the ways the game could have finished. By mapping those potential futures, he could compute each player's chance. A revolutionary idea. Use math to quantify an unplayed future. Pascal had taken the first step toward probability theory. While Pascal and Fermat had laid the foundation, the next major step came from a man who was fascinated by the bigger picture. About 50 years later, a Swiss mathematician named Jacob Bernoulli considered a different kind of question. He wasn't just interested in a single game or a single coin toss. He wanted to know what happens when you repeat an experiment over and over and over again. He wondered if the chaos of individual random events would eventually settle into a predictable, stable pattern. His work would give us one of the most important principles in all of probability. Bernoulli imagined that coin toss we talked about earlier. He reasoned that while a small number of tosses could give you almost any result, a very large number of tosses would tell a different story. He proved mathematically that as you increase the number of trials, the proportion of outcomes you actually observe will get closer and closer to the true underlying probability. If you flip a fair coin 1,000,000 times, the number of heads will be very, very close to 500,000. This powerful insight became known as the law of large numbers. It was the first formal link between theoretical probability and real-world results. This law was a monumental breakthrough. It meant that we could discover the hidden probabilities of the world simply by observing it. We didn't need to know the inner workings of a loaded die to figure out its bias. We just had to roll it many, many times. The results would speak for themselves. The law of large numbers gave us confidence that the data we collect from the world can reveal its fundamental truths as long as we collect enough of it. It transformed probability from a parlor game into an empirical science, a way of learning from experience. Bernoulli's work took years and was published after his death in a book called Ars Conjectandi, or The Art of Conjecturing. It was a fitting title. He had given humanity a formal method for making educated guesses, for turning conjecture into near certainty. He showed that even in a world full of random events, there is an underlying order that reveals itself through repetition. The law of averages, as it's sometimes called, is not a guarantee for any single event, but it is a promise that over the long run, chaos gives way to predictability. This idea would become essential for everything from insurance to scientific polling. The next great leap in our story came from a quiet English minister named Thomas Bayes. His work, done in the mid-18th century, addressed a different but equally profound question. While Bernoulli showed how to find a probability by repeating an event many times, Bayes wondered about something else. How should we change our beliefs when we encounter new evidence? This is something we do intuitively all the time. If the sky is cloudy, you might believe there's a 30% chance of rain. But if you then hear thunder, you update your belief. The chance of rain suddenly feels much higher. Bayes wanted to turn this intuitive process into a formal, mathematical rule. He developed a simple but incredibly powerful formula that does exactly that. Bayes' theorem provides a way to combine your prior belief with new data you observe. It tells you exactly how to adjust your confidence in a hypothesis in light of new evidence. It is a mathematical engine for learning. You start with an initial guess, you gather some information. As we move into the 19th century, the story of probability expands. It leaves the realm of games and individual beliefs and enters the world of society. Thinkers started to realize the same laws that governed a coin toss could also describe human populations. A Belgian astronomer and statistician named Adolphe Quetelet was a pioneer in this field. He began collecting vast amounts of data on people: height, weight, chest measurements, moral actions like crime rates. He wanted to see if there were patterns in the human condition itself. What Quetelet found was astonishing. He discovered these human characteristics were not completely random. Instead, they tended to cluster around an average value, with fewer people at the extremes. When he plotted this data on a graph, it formed a symmetrical, bell-shaped curve. This shape had been studied by Abraham de Moivre and Carl Friedrich Gauss. It is what we now call the normal distribution, the bell curve. By the late 19th and early 20th centuries, the tools of probability and statistics were becoming more widespread, but they were still a somewhat disorganized collection of ideas. This began to change with the work of two towering figures in England, Karl Pearson, Ronald Fisher. They are the architects who took the foundational concepts and built a rigorous, coherent structure around them. They created the formal methods and tests that defined the field of statistics for much of the 20th century and are still widely used today. Karl Pearson was a brilliant and sometimes cantankerous mathematician who believed deeply in the power of data. He worked to develop a whole host of new statistical tools. He gave us concepts like the standard deviation, a measure of how spread out data is from its average, and the chi-squared test, a way to determine if your observed results match what you expected. Pearson was driven by the idea that science should be based on cold, hard facts and statistical evidence. He founded the world's first university statistics department and the influential journal Biometrica, creating a home for this new science. Following Pearson came Ronald Fisher, arguably the single most important figure in the history of statistics. Fisher was a genius who made fundamental contributions across genetics and statistics. He revolutionized the way scientific experiments are designed and analyzed. He gave us the analysis of variance, ANOVA, a powerful method for comparing the effects of different treatments in an experiment. He also championed the idea of randomization in experiments and introduced the concept of statistical significance, including the famous p-value as a way to judge evidence against a hypothesis. Together, Pearson and Fisher created a formal framework for statistical inference. They developed the methods that allow a scientist to take a small sample, a handful of patients in a clinical trial, or a few plots of land in an agricultural experiment, and draw conclusions about a much larger population. Their work provided the mathematical machinery for the scientific method itself. It gave researchers a clear, objective set of rules for testing ideas and separating real effects from random chance. This was the moment statistics truly came of age as the grammar of science. For centuries, the growth of probability and statistics was limited by one major factor: the sheer difficulty of calculation. The ideas of Bernoulli, Bayes, Fisher, but applying them to large data sets required a mind-numbing amount of manual arithmetic. A single complex analysis could take a team of human computers weeks or even months to complete. This practical constraint meant that the full potential of these methods remained locked away. The world was generating more data than it could possibly analyze. Everything changed with the invention of the electronic computer. The middle of the 20th century marked a new beginning. Suddenly, calculations that were once prohibitively slow could be performed in seconds. The computer didn't invent new statistical theories, but it unleashed the power of the old ones. It allowed statisticians to apply their methods to datasets of a size and complexity that were previously unimaginable. The bell curve could be found not just in a few hundred measurements, but in millions of them. The law of large numbers could be seen in action on a massive scale. This newfound computational power fueled an explosion of new techniques and applications. Methods that were theoretically possible but practically impossible, like the iterative algorithms based on Bayes' theorem, fields like data science, machine learning. An algorithm could now learn from millions of examples of spam emails to build a nearly perfect filter. It could analyze the purchasing habits of millions of customers to recommend a new product. The computer turned statistics from a descriptive tool into a predictive one. Well, this era, our era, is defined by data. We live in a world where vast streams of information are generated every second, from social media posts, financial transactions, medical sensors. The modern challenge is no longer about collecting data, but about making sense of it. The principles developed by thinkers over the last 350 years are now more relevant than ever. They are the intelligence inside the machine, the logic that allows us to find patterns, make predictions, and automate decisions in this new digital deluge. The computer gave statistics a new, powerful engine to drive it into the future. The power of probability and statistics is immense. It has given us vaccines, safer cars, more accurate weather forecasts, and a deeper understanding of the universe. But this power is a double-edged sword. The same tools can uncover truth, and they can also mislead, intentionally or not. Averages can hide important details about individuals in a group. Correlations can be mistaken for causation, causing us to draw false conclusions. A beautifully crafted chart can distort reality. One of the greatest challenges is bias. Data often isn't a perfect reflection of the world. It can be skewed by how we collect it, who we collect it from, and what we choose to measure. Facial recognition trained on one demographic may perform poorly on others. Medical studies with narrow participants may not apply to everyone. The old saying holds true: garbage in, garbage out. A sophisticated model-fed biased data yields a sophisticated form of bias. Our minds aren't naturally good at statistical thinking. We see patterns in randomness. We prefer compelling stories over dry data. That makes us vulnerable to misuse. A politician might cherry-pick data. A company might show a misleading graph. The p-value, intended as scientific judgment, is often misused as a hard threshold, which has led to reproducibility crises. Learning to use these tools needs more than math. It needs care, wisdom, and a deep sense of responsibility. Ask critical questions about data. Where did it come from? What biases might it contain? What stories is it not telling? Be humble. Probability rarely gives absolute certainty. It gives a measure of confidence, a guide for belief, but leaves room for doubt. Responsible use requires a sharp, skeptical, and ethical mind. From a gambler's puzzle about dividing a pot of gold, a remarkable story has unfolded. We have seen how a few simple questions grew into a powerful scientific language. This journey took us from the letters of Pascal Fermat, who first gave us a way to measure chance. Bernoulli. We saw how Bayes gave us a formula for learning from evidence, and how Quetelet found the predictable patterns of the bell curve in the fabric of society itself. We then witnessed the rise of formal methods with Pearson Fisher, who built the rigorous framework that allowed science to test its ideas with confidence. And finally, we saw how the computer unleashed the full power of these ideas, giving birth to the data-driven world we live in today. Probability and statistics are no longer obscure branches of mathematics. They are the silent engines that power our modern lives, from the medical trials that ensure our medicines are safe, to the economic models that guide our governments, to the algorithms that shape what we read and buy. Yet, as we have seen, these tools are not magic. They are powerful, but they demand our vigilance. They can be misused, and they can mislead us if we are not careful. The challenge for us is to become better citizens of this data-rich world, to learn to think critically about the numbers and claims that surround us every day. We must appreciate the power of these methods to reveal the truth, while remaining keenly aware of their limitations and their potential for harm. The goal is not to be ruled by the numbers, but to use them wisely to make better decisions. And so, the story is not over. It continues to be written every day in laboratories, in businesses, and in the vast networks of our digital world. New methods are being developed, and new questions are being asked. As long as there is uncertainty in the world, we will continue to seek new ways to understand it, to measure it, and to navigate it. The journey that began with a roll of the dice in 17th century France is far from finished. The next chapter, filled with challenges and discoveries we can only begin to imagine, is waiting to be written.